Hello and welcome to Chapter 18 on the deaths of stars. We'll first start out with the lifespan of stars between zero point 0.4 and zero point 0.8 solar masses. So a red giant shines by shell fusion, the inert core shrinks and the outer layer expands. Luminosity increases and surface temperature decreases, so the star moves up and to the right on the HR diagram. Core helium fusion begins with the helium flash. The star now shines by shell hydrogen fusion and core helium fusion. The core expands and the outer layers shrink. Luminosity decreases and surface temperature increases, so the star moves down and to the left on the HR diagram. Eventually, all of the core helium is used up. The star now shines by shell hydrogen fusion and shell helium fusion. The core shrinks and the outer layers expand. Luminosity increases and surface temperature decreases, so the star moves up and to the right on the HR diagram along the asymptotic giant branch. Eventually, the star sheds its outer layers to form a planetary nebula. zero point 0.4 to 0.8 solar masses are called low mass stars, and greater than 0.8 or 0.4 to 8, not 0.8, sorry, are called low mass stars, and greater than 8 solar masses are called high mass stars. Once helium shell fusion commences, the star expands and the star ascends the HR diagram and to glow brighter than before. The sun will expand to a radius about 1 AU, while an 8 solar mass star will have a Mars with a Mars-sized orbit, or the orbit of Mars will be the size of the star, with a luminosity of 10,000 times that of the sun, and classified as low-temperature red supergiant. Asymptotic giant branch stars have a hydrogen fusing shell, a helium fusing shell, and a carbon-oxygen core, which does not have any fusion whatsoever. AGB self-destruction. Giant stars emit strong stellar winds. During their initial ascent up the giant branch, stars lose as much as 30% of their masses. On the asymptotic giant branch, they lose even more mass, often surrounding themselves with thickening cocoons of gas and dust. A star of the sun's mass loses about 10 to the negative fifth solar masses, or about 1/10,000th of its mass per year, eventually dumping half of its mass back into space. And I don't think it's actually 10,000th, I think it's 100,000. The low mass AGB star is compressed until its core of carbon and oxygen becomes degenerate, meaning that the electrons provide a growing repulsive force that stops its contraction. The final stage through which a low mass star begins with thermal runaway, meaning a rapid rise in temperature in the helium cell. Just like the helium flash earlier in its life, this process occurs because of the triple alpha process, or the helium core plus the helium core plus the helium core yielding carbon plus gamma, and then helium core plus carbon yielding oxygen, I believe. Or it could be the other way around. I would double check my last video. It is extremely sensitive to temperature, and as the temperature goes up slightly, the fusion rate skyrockets. This increase in energy output from the thin helium fusing shell, called the helium shell flash, expands the star, thereby briefly decreasing the temperature in the shell and slowing the rate of fusion. These stars undergo several helium shell flashes as its shell thickens. During each flash, the helium shell's energy output jumps 1,000-fold. Eventually, the outer gases sufficiently recombine, the opposite of ionization, and emit photons which eject more and more of the star's outer layers into space. When enough of the gas has left the star for the core to be visible, the expanding dust and gases are considered to be a planetary nebula. The star moves to the left across the HR diagram, and low-mass stars lose as much as 80% of their mass by shedding outer layers. We here see a bipolar planetary nebula where a central star sheds its outer layers into two different directions, nitrogen-rich blobs of gas, which cause there to be a nebula which is going from one side, or is going out in opposite directions on the two poles and is therefore called bipolar. The exposed carbon-oxygen cores of low-mass stars are stable objects supported by electron degeneracy pressure. Such burned-out hulks are called white dwarfs. They are very dull compared to what they used to be. Here we have 3 tracks for red supergiants of different different masses. They become white dwarfs along track A for a giant of 3.0 solar masses, track B for a red supergiant of 1.5 solar masses, C for a red supergiant of 0.8 solar masses. Occasionally, a star in the sky becomes between 10 to the 4th, which is actually 10,000 times, and 10 to the 6th, or a million times brighter than it normally is, and then declines over the course of several months. These are called novae, and are about 20 to 50, and about 20 to 50 are estimated to occur in the Milky Way annually. And here we see the luminosity as it suddenly just peaks up, and then gradually declines over the course of several months. It is caused by material from a star accreted onto a companion white dwarf. When enough accreted material builds up, thermonuclear reactions occur on the white dwarf surface, creating a burst of visible light. The nova then fades over several weeks. Whereas the nova only removes hydrogen and helium that build up on the surface of the white dwarf, some of these stellar remnants actually blow apart completely. This is called a Type 1a supernova, and it occurs in high mass, meaning close to the Chandrasekhar limit white dwarfs that are in binary systems. In one model, the white dwarf's mass approaches the Chandrasekhar limit, while the companion is still fusing, causing a runaway carbon and oxygen fusion, which produces so much energy that the white dwarf explodes. In another model, both stars are white dwarfs, as the original white dwarf pulls enough mass to cause the other to become one. The two combine and collapse. This seems more likely as a Type 1a supernova in 2014 density X-ray emissions, which would be expected from the first model. A Type 1a supernova is powered by nuclear energy. What we see is the fallout from a gigantic thermonuclear explosion, which produces a wide array of elements, including silicon, copper, calcium, sulfur, iron, cobalt, and nickel. Especially abundant is a radioactive, unstable isotope of nickel that decays into a radioactive isotope of cobalt. Most of the electromagnetic display of a Type 1a supernova results directly from the radioactive decay of this nickel and cobalt. There are no hydrogen lines because the white dwarf from which it came was virtually free of hydrogen. Stars with more than 8 solar masses heat their cores enough to cause carbon and oxygen to fuse. When helium fusion ends in the core in a star more massive than 8 solar masses, the inward pressure created by the gravitational force from its outer layers compresses the carbon-oxygen core, driving the star's central temperature above 600 million Kelvin. Now carbon fusion begins, producing such elements as neon and magnesium. When a star compresses itself enough to elevate its central temperature to 1.2 billion Kelvin, neon fusion occurs, creating oxygen and magnesium. When the central temperature of the star reaches 1.5 billion Kelvin, oxygen fusion begins, producing sulfur, silicon, and phosphorus. The process of converting lower mass elements into higher mass ones is called nucleosynthesis. This causes each successive stage of the core to have fewer absolute atoms as smaller atoms fuse into larger ones. The star expands to become a luminous supergiant about as wide across as Jupiter's orbit. Eventually, the core is converted entirely into iron. Iron cannot fuel further thermonuclear reactions, and the core must support the outer layers exclusively by degeneracy pressure until the continual addition of fresh iron causes the degeneracy pressure to suddenly fail and the core collapses. In roughly a second, the central temperature exceeds 5 billion Kelvin. Gamma ray photons associated with this intense heat have so much energy that they begin to break apart the iron nuclei, a process called photodisintegration. In another second, the electrons in the core combine with the core's protons and become neutrons, releasing neutrinos, which are produced at high enough densities to provide a pressure pushing out from the core. Another second passes, and the core reaches nuclear density of 4 times 10 to the 17th kilogram per meters cubed, the density of an atomic nucleus, and it suddenly stiffens, halting the collapse so abruptly it rebounds and begins rushing back out in core bounce. The model predicts that, during this critical stage, the star's unsupported layers of shell-fusing matter outside the core are plunging inwards at up to 15% of the speed of light. The outward-flowing neutrinos in the rebounding core slam this matter. The impact stops the core's rebound while causing the infalling matter to reverse course. In just a fraction of a second, a tremendous volume of matter begins to move back and up towards the star's surface. This matter accelerates rapidly as it encounters less and less resistance, and soon it forms an outgoing shock wave analogous to the thunder created by a lightning flash. After a few hours, the shockwave reaches the star's surface, lifting the star's outer layers away from the core in a colossal blast. The star becomes a Type II supernova. A supernova is often 10% as bright as all of the other stars in its galaxy combined. Many of the elements with more protons than iron are created during supernovae. Recall from Chapter 4 that neutrons can transform into protons by emitting an electron. As the layers of a massive dying star are blasted into space, they are compressed by so much that the neutrinos and the shockwave that the neutrons are forced into the elements that they have created as the star evolves. Packed with extra neutrons, many of these nuclei are unstable. As a result, neutrons begin emitting electrons, a process that converts these neutrons to protons. Once this occurs, the nucleus is no longer the element it was a moment before. In observations connected with supernovae, astronomers have detected particles flying through space at speeds that exceeds 90% of the speed of light. These high-speed particles are called cosmic rays or primary cosmic rays. They were named rays before their true identity as particles was known. About 90% of cosmic rays are protons, hydrogen nuclei. A few percent of cosmic rays are electrons and positrons, positively charged electrons. Less than 1% of cosmic rays are nuclei of more massive non-hydrogen elements. Cosmic rays showers are caused by these particles hitting gas in the Earth's atmosphere and creating a cascade of lower energy particles called secondary cosmic rays. Cosmic rays are responsible for the formation of some of the lower mass elements found throughout the cosmos, specifically some lithium and most of the beryllium and boron. The cosmic rays collided with higher mass elements, splitting these into lower mass elements in a process called cosmic ray fission. Most of these elements found on Earth were created by cosmic ray fission in the interstellar gas and dust from which the solar system formed. When stars that initially had between 8 and 25 solar masses explode as supernovae, their rebounding neutron cores are stopped by the outer layers into which they slam. These cores are then recontract and remain intact as highly compressed clumps of neutrons called neutron stars. Isolated neutron stars resulting from these explosions are stable nuclear or stable stellar remnants with masses between 1.25 and about 3 solar masses. Neutron degeneracy pressure supports remnant cores made out of neutrons that equations predict is even greater than electron degeneracy pressure, and thus allow stellar remnants composed of neutrons and with masses beyond the Chandrasekhar limit to be stable. Neutron star matter is 200 million times denser than that in a white dwarf. Jocelyn Bell found repeating pulses from radio source LGM1 or Little Green Men 1, but further discoveries led to them being known as pulsars. And here we see the intensity of electromagnetic pulses that are coming in at a very constant rate, which initially led to them being thought to be created by aliens, but are now known to be created by pulsars, which are going to be explained in the next slides. The center of the Crab Nebula supernova remnants is a pulsar called the Crab pulsar. Spinning period of 0.033 seconds would cause something as wide as the white dwarf to fall apart, leaving the only explanation to be neutron stars, which were up until that point thought to be very unlikely. A rotating magnetic field explains the pulses. Where, as we see, pulsar is precessing or rotating around or having its axis rotate around another axis very quickly, so that the magnetic field inside of it is pointing to one side at one moment, and then 0.033 seconds later, in the case of LGM1, pointing towards or half of 0.033 seconds, because it's only moving through half of its precession, is pointing towards us at another moment. This is called the lighthouse model because it is for the same reason that you see a lighthouse coming or a lighthouse beam pointing towards you at some point and away from you at another point where you won't see the lighthouse beam coming towards you. If the neutron star is very hot, around 10 to the 11th Kelvin, and spinning very fast, 100 times a second, when it forms, convection occurs throughout the neutron star just as it does for red dwarfs. This inward and outer convective flow of matter combined with the spin generates extra magnetic fields via the dynamo effect. Combining the neutron star's two magnetic fields yields a field 10 to the 15 times greater than the field at Earth's surface. Resulting object is called a magnetar and its effects are dramatic. The magnetic fields of a magnetar are so strong that they can cause the neutron star's surface to buckle and emit stupendous bursts of X-rays and gamma rays, along with photons and other wavelengths that last for fractions of a second. Such magnetars are called soft gamma ray repeaters, or SGRs. Soft means low energy. Even so, soft gamma rays are very powerful photons. Interacting with surrounding gases, the magnetic fields of a magnetar rapidly slows the neutron star's rotation rate. After 10 to the 4 years, or 10,000 years, the body spins only once every 10 seconds, and the SGR activity subsides. 23 magnetars have been observed since 1998, including one in 2004 that released the brightest flash ever seen from outside our solar system. Its photons scattered off the moon and lit up Earth's atmosphere. Observations of magnetars reveal that they generate the brightest supernovae up to 5 times 10 to the 12th luminosity of the sun, or 5 trillion times brighter than the sun is today. That extra brightness is powered by the energy stored in magnetars' rotations and magnetic fields. In 2006, radio astronomers discovered yet another type of emission from rotating neutron stars called rotating radio transients, or RRATs. These objects gave off bursts of radio and other emissions that last a few thousandths of a second, turn off for minutes or hours, and then briefly spring back to life. The neutron stars involved rotate slowly compared to most pulsars, spinning about once every 0.4 to about 10 seconds. The most promising explanation at present is that these are older pulsars or magnetars that have slowed down. Neutron stars are not composed solely of neutrons. Astronomers have developed a theoretical model for the surface and internal structure of neutron stars. A neutron star's interior has a radius of about 10 kilometers, with a core of superconducting protons and superfluid neutrons. A superconductor is a material which electricity and heat flow through without the system losing energy, whereas a superfluid has a strange property that flows without any friction. Both superconductors and superfluids have been created in the laboratory. Surrounding the neutron star's core is a layer of superfluid neutrons. The surface of the neutron is a solid brittle crust of dense nuclei and electrons about 3/4 of a kilometer thick. The gravitational force of the neutron star is so great at its surface that climbing a bump there just 1 millimeter high would take more energy than it takes to climb Mount Everest. Binary pulsars have companion stars. Many pulse mass onto themselves in a way that causes them to speed up rotation, similar to how pulling in a figure skater's arm will cause faster rotation up to nearly 1,000 times per second, called millisecond pulsar. They can kill their partners, and these are called Black Widow pulsars. They are also pulsars orbiting each other, which can test Einstein's theory of general relativity. Superluminous supernovae, or hypernovae, are more than 10 times brighter than Type 1a and Type 2 supernovae. Each of these explosions shines brightly for months rather than weeks, and they are often associated with bursts of gamma rays. Furthermore, many hypernovae are observed to have pairs of jets of gas shooting out at high velocity in opposite direction. They have disks of gas and dust orbiting them that feed the jets. One thing that appears likely is that they all occur as a result of the end-stage evolution of massive stars. You also have supernova impulsors, which are stars that undergo recurring explosions as power of some supernova, but which don't completely destroy themselves with each explosion. Binary neutron stars may create many of the heaviest elements in the universe and are possible sources of X-ray pulses. X-ray bursts are caused when material from a star accretes into a companion neutron star. When enough accreted material builds up, thermonuclear reactions occur on the neutron star's surface, creating a burst of X-rays. The X-ray bursts fade within a matter of seconds.